Thank you very much. So it's a great pleasure to be here today to tell you about our work, experimental work, on ultra-strong light matter coupling in high-Q terahertz cavities. So we're doing spectroscopy of condensed matter systems in the terahertz range, or in terms of photon energies, mil-eV, wavelengths, in terms of wavelengths, hundreds of microns, and in terms of wave numbers, 33. This range is very, very rich in solid-state physics. There are lots of elementary and collective excitations, phonons, plasmons, magnons, cyclotron resonance, superconducting gap excitations. So the idea is to strongly couple with these excitations in a cavity. So we have constructed high-Q terahertz cavity. So our typical line width, the photonic decay rate is 2.5, a few gigahertz, whereas the center frequency of the cavity is a few terahertz. So the order of magnitude of the Q factor of cavities is about 1,000, corresponding to a photon lifetime of about 70 picoseconds and a finesse of 100. So this is all happening in the terahertz frequency range. So let me first tell you about our cavity design. So what we use is plates of silicon, intrinsic high resistivity non-doped silicon, whose absorption coefficient is very, very small in the terahertz range. But it has a large index. So basically, our cavity is a DBR cavity. And so we have alternating layers of silicon, vacuum, silicon, vacuum. So high index material silicon, whose index is 3.42, and the vacuum is 1. So there's a huge contrast between the two materials. So just by having two layers, you can easily calculate the reflectivity to be 97%. If you have three layers, the reflectivity is already 99.7%. So most of the work we have done so far has been done with 2 or 3 layers of silicon. And what's great about this design is this is an ideal laboratory, terahertz cavity laboratory for condensed matter systems. So here inside we can place any material. This is a very good platform for studying ultra-strong light matter coupling in condensed matter systems. We can measure bulk samples or also film samples on a terahertz transparent substrate. So the main topic of this talk is ultra-strong light matter coupling. So we study polaritons, as in the first 2 talks in this session. And so basically we have omega 0, which is the photonic mode frequency in the cavity. And then by some means we tune the matter frequency. Okay? Often in this case, in our case, magnetic field. Okay? So the matter frequency changes. And they meet here, and then they show anti-crossing behavior. And the coupling rate we denote by G, and the resonance frequency omega 0. So polaritons appear in the strong coupling regime, where the light matter coupling rate G is larger than the line width, or gamma and kappa, matter decay rate and the cavity decay rate. So in the frequency domain, you can see Rabi splitting. But ordinarily, the resonance frequency, omega 0, is much, much larger than G, right? Orders of magnitude larger if you look at exciton polaritons, typically. Okay? But what we are talking about here is not just strong coupling regime, but ultra-strong coupling regime, where this condition is not satisfied, which means that the coupling rate or the Rabi frequency becomes a significant fraction of the transition frequency itself, or sometimes it's even larger than the transition frequency. There's no clear-cut definition about the ultra-strong coupling regime, but let's say 10%. Okay, so when G becomes larger than 10% of the transition frequency, we call it the ultra-strong coupling regime. So let me first tell you why we're working in the terahertz frequency range. So if we start with a simple two-level atom system in a cavity and resonating, interacting with a single mode of photons at two states 0 and 1 with a transition energy omega 0, the coupling G, so the Rabi frequency is the product of the dipole moment of the transition and the amplitude of the vacuum fluctuation field in this cavity at this particular frequency. So if you divide G by the photon frequency omega 0, you get this expression. So in order to make this large, G over omega 0 large, you want to have a large dipole moment transition which exists in the terahertz range. There are many transitions in solid state materials which has huge dipole moments. And you want to go to small frequencies. Instead of optical frequencies, you can go to far infrared terahertz frequencies. Okay, so that's why we are doing this in the terahertz range. Once this is satisfied, what happens? So first of all, the rotating wave approximation breaks down, which leads to a finite frequency shift known as the Bloch-Seeger shift. Second, the diamagnetic term, or the A squared term in the Hamiltonian, which is usually negligible, becomes not only negligible, and also it plays a major role in determining some of the physical processes that I'm going to talk about today. And more interestingly, the ground state properties are significantly modified through non-perturbative coupling with the vacuum electric field. Specifically, as shown by Chuti and co-workers in 2005, the nature of the ground state becomes non-classical. It's a two-mode squeezed vacuum state, and so the ground state acquires finite amplitude of both vacuum field and the matter excitation. These are virtual fields, but if you can quickly change the condition, it's predicted to be possible to release these virtual photons as real photons. And most excitingly, it had a very, very heatedly debated possibility of the Dickey superradiant phase transition occur. So I'll discuss all these in this talk. So for the next 10-15 minutes or so, I want to introduce you to a specific system where we demonstrated ultra-strong coupling, showing the breakdown of the rotating wave approximation, showing a clear vacuum Bloch-Seeger shift. So here, in the middle of this cavity, we inserted a two-dimensional electron gas, high mobility two-dimensional electron gas in gallium arsenide, which is placed on top of a silicon substrate. And we did terahertz transmission experiments in the presence of a perpendicular magnetic field in the Faraday geometry. So the magnetic field is applied this way, and the terahertz beam propagated along the magnetic field direction. So the magnetic field quantizes the electronic structure into Landau levels. So what we have is a two-dimensional electron gas, which is quantized due to the perpendicular magnetic field into Landau levels, which is placed inside this high Q terahertz cavity. And so this 2DEG has a certain Fermi energy. So the coupling we're looking at is, so the transition we're looking at is a transition from the highest occupied Landau level to the lowest unoccupied Landau level. Okay, so in the case of gallium arsenide, it has a very parabolic band with a constant effective mass. So each Landau level increases in frequency linearly with increasing magnetic field. So when this transition cyclotron resonance frequency increases with increasing magnetic field, when it meets the the photon frequency we see at Rabi splitting. Okay? So this particular topic was pioneered by Jerome Feist in the audience, and he's using metamaterial cavities and on various semiconductor 2D structures, and reporting huge values of G over omega 0 parameters. So our cavity design is different. So we are using the 1D photonic crystal cavity that I mentioned at the beginning. So this shows you a little bit more details about our design. So we have silicon, vacuum, silicon, vacuum, silicon, vacuum. Right? So here we have a central piece of silicon on which we have a two-dimensional electron gas gallium arsenide attached. So as you can see, the field distribution is designed in such a way that the peak of the field coincides with the location of the two-dimensional electron gas. And this is one of the multiple photonic modes in the cavity. So this mode is centered at 0.4 terahertz. This is the first mode. We have the second mode and third mode at different frequencies. And within the frequency bandwidth of a terahertz spectrometer, so these three modes exist. And each mode appears in the middle of a photonic stop band. Okay, so there's no transmission here, and inside we have this mode. Okay, if you expand it, you see that the full width is very, very sharp. The full width at half maximum is 2.3 gigahertz. So we have a long time window to ensure that we have enough spectral resolution to see this. Okay, so here this is the first mode, this is the second mode, this is the third mode. Okay, so there are three modes at different frequencies, and then we do magnetic field scans. The magnetic field, as the magnetic field changes, the cyclotron resonance frequency increases linearly. And when it hits the first photonic mode, we see this anti-resonance, anti-crossing, and this is the second photonic mode, this is the third photonic mode. What you see here, that mu, the index nu, is the Landau level filling factor defined by this. So this tells you at a given magnetic field how many Landau levels are occupied. Right? So as we increase the magnetic field, the degeneracy of each Landau level increases. So the filling factor becomes smaller and smaller. So and eventually we can go to the fractional quantum Hall regime, but we haven't been there. So all our measurements have been done in the integer quantum Hall regime. So the first thing we wanted to know was whether there's any systematic dependence on the filling factor, whether the Rabi splitting depends on the filling factor. So we found a very small dependence. Okay, so the 2G is 72 gigahertz at nu equals 12, 66 gigahertz, and 60 gigahertz. So as we decrease the filling factor, the Rabi splitting increases. No, I'm sorry, decreases slightly. Okay. It turns out that there's a lot of cancellation happening. So we can easily estimate the vacuum Rabi splitting in this case. This is the dipole moment times the vacuum fluctuation electric field strength and the square root of n behavior. But D depends on the magnetic length and the filling factor, and the magnetic length depends on the cyclotron frequency, and the vacuum fluctuation field at this cyclotron frequency obviously depends on the magnetic field. So there's a lot of cancellation. Eventually 2G is independent of the magnetic field. There's no explicit magnetic field dependent except this LZ, the cavity mode length or mode volume changes between this. That's why the 2G value is changing. But there's no explicit magnetic field dependence. Let me show you more details about the experimental spectra. So here I'm showing you transmission spectra taken at different magnetic fields from -3 Tesla to +3 Tesla. as you can see, we have a very narrow transition which is moving rapidly with the magnetic field. So the first thing I want to point out is this. So the sign of the magnetic field is important because we are using circularly polarized terahertz radiation. So because the electrons are charged, so when you apply a magnetic field, the electrons are moving in one direction. So when you have two circular polarizations, only one of them is supposed to couple with the cyclotron motion. So that's what I mean by cyclotron resonance active. So active means that the direction of the circular polarization matches the motion direction of the cyclotron motion of the electrons. Okay? So therefore, there's zero detuning point. So this is the cyclotron frequency. This is the photonic mode. This crossing occurs on the positive magnetic field side. Okay? And so this is omega c, electron cyclotron resonance frequency. This is the photonic mode, which is independent of the magnetic field. And the difference between the two is the detuning in this case. And the Rabi splitting depends on the detuning. And the detuning, the on resonance Rabi frequency is 2G. So this is what we get. Around 1 Tesla, positive 1 Tesla, we get this zero detuning. And first of all, I want to point out that this Rabi splitting is much, much larger than the line width. Right? So the frequency from here to here is 2G, and the width, which is given by some sort of average between the matter decay rate and photon decay rate, is given by the line width. And in fact, the so-called cooperativity, 4G squared over gamma kappa is 3,513, which is extremely large. So we're definitely in the strong coupling regime in the usual sense. And in addition, 2G over omega 0, this is the Rabi frequency divided by the center frequency. This is the so-called normalized Rabi frequency is 72%. So we are in the ultra strong coupling regime. And I want to direct your attention to this behavior. So this is the most important feature of this plot. Basically, what's happening here, right? So here, as I already mentioned, the magnetic field is applied in the opposite direction, right? So the electrons are moving this way, but the circular polarization, light is moving in the other direction, right? So in a classical sense, they shouldn't interact, right? And this happens because we are in the ultra-strong coupling regime. Right? So in fact, if we continuously tune this parameter, increase this parameter G over omega 0, in the weak coupling regime, everything should be happening on the positive side. Right? So this is the upper polariton, lower polariton, everything should be happening in the vicinity of this zero detuning point. Nothing should be happening on the negative magnetic field side. But as we increase this parameter, this anti-crossing behavior becomes larger and larger and larger, and eventually it spreads over into the negative magnetic field region. So this is what's happening. So qualitatively speaking, that's what's happening. But a little more quantitatively, let me explain to you how we can model this, starting from the most basic JC Hamiltonian, the matter term, and the light term, and the interaction term. This is within the rotating wave approximation. But already in 1940, it was pointed out by Bloch and Seeger that when the intensity of light becomes large, or coupling becomes large, sufficient large, the rotating wave approximation breaks down, which means that the counter-rotating terms need to be included. So within the same Hamiltonian, we have to add these counter-rotating terms. In addition, we have to add these so-called A-squared terms. Okay, so all these are photon parameters, photon operators, but the coefficient eta depends on the coupling constant. Right? So this is purely photonic, but then this doesn't exist if the coupling becomes zero. So this is sort of the schematically, I'm showing you what's needed to be included in order to explain our data. But real theoretical calculations were done by Motoaki Bamba at Osaka University, and all the details are provided in this recent archive paper. So, so this is specifically for our system, two-dimensional electron gas in a perpendicular magnetic field in a cavity. And so there are 4 terms, 1, 2, 3, 4. This is the matter Hamiltonian, Landau quantized electrons, and the cavity, the photonic modes. We have multiple photonic modes included, and so we explicitly include the circular polarization state, polarization. And then the interaction Hamiltonian, which contains both the co-rotating and counter-rotating contributions, and the A squared term. So the great thing about this is we can turn on and turn off different terms in the Hamiltonian, and then compare with the experiment to see what each term is doing to the behaviors. So here on the left I have experimental data. On the right I have theoretical calculations, and the CRI mode is folded onto the positive magnetic field side so that we can see everything: upper polariton, CRI, and the lower polariton. So here I'm showing you the theoretical results without counter-rotating terms, without A squared. So as you can see, the agreement is poor. But first I want to introduce the A squared term to see what it does. Okay, so this is with the A squared term. This is without. With, without, with, without. So as you can see, what it does is basically the A squared term, it increases all the 3 modes. Right? So basically some sort of 0 point energy is increased by including this A squared term. And next I will introduce the counter-rotating terms. So this is with, without, with, without, with, without. Basically what you see is that the counter-rotating terms affect only the cyclotron resonance in active mode. That makes sense, right? Because physically that's where the magnetic field is negative, so the electrons and photons are moving in the opposite way. That's where the counter-rotating terms play the major role. So only when we include both the A squared term and the counter-rotating terms, we get satisfactory agreement between the theory and experiment. So, I showed you this already, but basically the vacuum block Seeger shift appears only on the CRI side and only in the ultra-strong coupling regime.
So excuse me, John, can
Yes.
you go back 1 slide?
Yes.
So just looking at it by eye, it appears that there's a moderate quantitative difference in the dispersion of the upper polariton mode, even after everything is included, right? That the upper branch, or is it that the magnetic field scales are different?
You mean between upper polariton and lower polariton?
No, I was just comparing theory and experiment.
Yeah, I'm sorry.
The field scale is different.
Oh,
by a
I'm
factor
sorry.
of 2.
The field scales are different by a factor of
Oh,
2.
yeah.
I'm sorry. That's the reason. Excuse
Okay.
me. Okay. Sorry. Yeah.
Right. Okay.
Okay. Sorry. Yeah. So yeah. Okay. Because you would think that should agree essentially perfectly.
Yeah.
Okay.
It does. I think it does.
Okay.
Yeah.
Sorry. Yeah.
Any other questions? So let me quickly summarize what I have talked about so far. So terahertz cavity QED. So we have developed high Q terahertz cavities that are easy to fabricate and usable for studying a variety of materials at low temperatures and high magnetic fields. So this is a very useful environment for studying condensed matter physics in the presence of strong light matter coupling. And specifically, we studied high mobility 2DAG in the integer quantum Hall regime, observing coherent light matter coupling which produced Landau polaritons in the strong coupling regime. And the ultra-strong coupling produced, and the combination of ultra-strong coupling and high Q and ultra-high mobility produced a record high cooperativity, 3 times 10 to the 2. And we observed a very clear evidence for the breakdown of the rotating wave approximation through the vacuum block Seeger shift. So basically, this cavity terahertz cavity QED is really exciting because It combines the three things: terahertz strong field physics, terahertz quantum optics, and terahertz condensed matter physics.
Yes.
Yes?
So in this experiment with this integer quantum Hall effect, are there any phenomena that rely on many-body physics? So do you need any many-body physics of electrons to understand your data, or it's all single particle?
So far, all the results we have reported can be understood within a single particle picture. So the next step is to explore more about the many-body aspects. And so that's what I want to talk about a little more. But the so the great thing about condensed matter systems compared to atomic systems is we are dealing with a huge number of particles. Right? So we have this massive many-body enhancement. First of all, this is even without including Coulomb interaction. This is just a sheer number of huge number of particles we're dealing with. So this clearly shows you that the vacuum Rabi splitting scales is proportional to the square root of the number of electrons. So here we change the electron density, different samples, and also in a single sample we change the density. So we have this so-called Dickey cooperativity. So this was already mentioned, but so the Tabis-Cummings or Dickey Hamiltonian within the rotating wave approximation. So instead of JC Hamiltonian, we have a collection of atoms, identical atoms, and by introducing this collective excitation bosonic operators, one can rewrite the interaction in this way. So this means that we can treat the system as a single atom with a huge dipole moment. So the collective system is responding to light together collectively. So this is called Dickey cooperativity. So again, so this can be enhanced by many orders of magnitude by using condensed matter system. This is exciting because we can chase the possibility of this Dickey phase transition, which was predicted in 1973 by two theory groups independently, Hepp and Lieb and Wang and Choi. So this new phase can appear when the coupling constant G becomes even larger than the transition frequency. So basically the Rabi frequency becomes larger and larger. So the lower polariton branch can become even lower in energy than the original ground state. And then a new ground state appears where the average number of photons becomes finite. So this axis is G over omega 0. So this average number of photons this is not photons you're putting in. This is coming out in the vacuum in the cavity. And this depends on both temperature and the coupling constant. So this new phase is predicted to exist at low enough temperatures below Tc and high enough coupling constant. So it's important to note that this transition occurs even at T equals 0. So this is, in more recent theoretical papers, this transition is discussed as a quantum phase transition, which occurs even at T equals 0. But this has been a very controversial issue among theorists. And so there's a no-go theorem already published in 1975, okay, from a group in Poland. So their criticism was very, very clear. So in the original 1973 papers, they did not include the A-squared term. And the point is, if you include the A-squared term, the lower polariton branch will never cross the ground state. It asymptotically approaches 0. But this question, whether it's possible to have this phase transition, has been discussed for many, many years. In 1978, 2004, 2007 by Jonathan Keeling, 2014, and more recently 2018, 2019. The theorists are still discussing. So these papers discuss if you're not careful, the gauge invariance is broken. There's some sort of gauge ambiguities in the ultra-strong coupling regime. And this paper appeared two months ago right, by Marco Pollini and Alan McDonald, again, talking about a no-go theorem. So the theorists are still debating. What I want to focus on is this paper. Okay, so Knight, Aronoff, and Shi in 1978. So all the other papers, they talk about electric dipole interaction. But this paper mentioned that we cannot rule out phase transitions based on magnetic dipole interactions. That's why we were stimulated by this, and we started looking at magnetic systems where magnons are important. Okay, so the specific system we're working on is a rare earth orthoferrite, and specifically erbium ion oxide. And there are two subsystems: ion subsystem, which is antiferromagnetically ordered at a very high temperature, and then erbium subspin systems. And so there are two magnetic subsystems inside this. Okay? So in the temperature range where we did measurements, the ions are antiferromagnetically ordered, but the erbium ions are independent. So we can see terahertz magnon excitations, and even at room temperature, the very beautiful terahertz coherent excitations, magnons can appear. Erbium ions, on the other hand, are independent. They show they have 4f electrons, and they have crystal field splittings and exchange splitting due to ion erbium exchange interaction. And then when you apply an external magnetic field, Zeeman splitting appears. And since the crystal is anisotropic, so it depends on the cut, A cut, B cut, C cut, and for each cut, there are two polarizations. So we see all these complicated terahertz spectra. We're basically doing atomic spectroscopy in a solid in the terahertz range. But the most important transition is this one. So this A transition, which is essentially an EPR, electron paramagnetic resonance. So we're just flipping the spin. So these spins are independent, not ordered yet. Okay. Yes, please.
Sorry, the oscillations that you showed before.
Yes.
Are taken with terahertz transmission spectroscopy, or
yes,
with Poincare Faraday rotation?
So this is simply terahertz transmission spectroscopy. So this antiferromagnet has small what do you call canting angle due to the Dzieloszynski-Muria interaction. So there's a macroscopic magnetization. So we can couple with the magnetization directly.
So do you generate the terahertz with optical rectification or
yes,
something else?
Right.
Okay.
Yeah, the optical rectification outside, not
outside,
the crystal.
Yeah, free space. Yeah.
Right. Yeah.
Okay. Thank you.
Yes. So basically, yeah. So this spin up, spin down transition. So they coincide, right? So as we change the magnetic field, the EPR frequency again changes linearly, okay? And then the magnon frequency exists, and when they meet, they show anti crossing behavior. So again, Motoaki Bamba developed this theory. The Hamiltonian, the original Hamiltonian looks like this. Okay, so it's very different from light matter interaction Hamiltonians, but after some transformations and approximations, this can be rewritten as this way. So the important point is that there's no A square term. Okay, so just the co-rotating, counter-rotating interactions exist, and we found that so in this paper we described that there is Dicke cooperativity. So this is promising. So we systematically change the number of spins, and then the vacuum Rabi splitting. This is the coupling between the EPR and magnons. This coupling increased, and as a function of square root, so linearly increased square root of the effective number of spins. Okay, so this is a rather unusual situation that Dicke cooperativity is happening in a very magnetic context with no light involved. Let me quickly finish this talk by talking about the third subject. This is not terahertz. Okay, so this is, but I wanted to talk about this because this is still related to cavity. So what we are studying is excitons. Exciton polaritons in the ultra-strong coupling regime in carbon nanotubes. So carbon nanotubes are one-dimensional semiconductors. We're just using semiconducting carbon nanotubes here, highly purified, 6.5 purified. It has a huge exciton binding energy on the order of 500 millieV, and very anisotropic because the nanotubes are aligned. So so this is embedded inside a cavity. There are two angles here. So this angle is the light incident angle, right? So by changing this, we can couple with finite momentum states of polaritons, right? As in any exciton polariton system. But what's unusual is we have this additional angle, phi. So this experiment was done at a fixed phi. So the phi is fixed, and then we scan theta. So this corresponds to in-plane momentum, and we have this a polariton splitting. And then we fixed theta here, and then changed the polarization angle. So this is interesting, right? Because so here when this angle is 90 degrees perpendicular, we lose the strong coupling, zero coupling. But as we gradually rotate the polarization, this splitting appears. So we have this a single system in which the apparent G depends on the polarization of the probe. Right? So if the polarization is perpendicular, we are weak or zero coupling regime. But then if the polarization is parallel to the nanotube axis, we have this strong coupling regime. And it becomes really interesting if we plot that dispersion relation, the entire dispersion as a function of kx and ky. So this is the traditional situation, the gallium arsenide. So energy versus kx and ky. This is isotropic in the plane. So no matter where you look, there's a gap. There's a gap between the photonic, between the upper polariton and the lower polariton. It's gapped throughout. But this is our situation. Right? So energy versus kx and ky, it's gapped only in a certain region of k space. Okay? So here, anti-crossing occurs. Here, crossing occurs. Okay? So this transition is rather unusual, right? So we're changing the angle like this. So initially, no gap, and then above here. So we see this. It turns out that there's an exceptional point. So here, and so there are two exceptional points in K space. Here, here, and here, here. Between these exceptional points, there's no gap. But above exceptional points, we have a gap, like this. And when the gap is large, when we are in the parallel regime, we again see huge. This is so then the splitting, the vacuum Rabi splitting is over 300 millieV. Okay, this is exciton, right? The 1E excitons, by the way. These are not really Frenkel excitons. 1E exciton, 300 millieV vacuum Rabi splitting, and by changing the thickness in this case, this is a highly densely packed nanotube films. By changing thickness, we're changing the number of nanotubes. But this, yes.
How well are they aligned? Must not
So
be so easy to get them perfectly aligned.
Oh yeah. So in this particular film, the nematic order parameter S is 0.7. So S equals 1 is perfect alignment.
Yeah.
In this case, it's 0.7.
So
but this is
we get even bigger gaps if you were perfectly aligned.
correct. Yes. So we have been making these films for some time, and this is a single chirality.
Yeah.
So that's unusual. So 0.7 is already impressive.
Yeah.
But when we have a mixture of metallic and semiconducting, sometimes we get S equals nearly 1.
So if I went to that exceptional point, if I had a higher resolution, will I still see the splitting, and then would that be a single point, or would I still get these 2 points?
Single point, let's say.
If you go to the previous picture,
Yes.
where you had. So how does the resolution of your setup dictate where you're seeing these exceptional points?
Spectral resolution. Let's see. Let me see if I understand the question. So, I mean, there's only one exception. So there's this point and this point are different,
Yes.
right? So
So basically, you're going from something that's aligned to something that's non-aligned, right? I mean, you're changing depending on the orientation of your nanotubes.
right.
Polarization.
Yeah, he's aligning, yes, exactly. So shouldn't it be a smooth transition?
Yeah, but if it was.
So first of all, so Motoaki developed the calculated the dispersions by solving the quantum Langevin equations within the input-output formalism, including the coupling G and the dissipation through gamma and kappa, and then he derived this analytic expression for the omega, plus and minus. And this is a complex frequency, and you can see that under certain conditions, the two solutions coalesce. And we used this equation to fit our experimental data to show this behavior. So within this, we have only one mode.
Okay.
So here it is like that.
Okay, so just asking sort of details of the fit there, because of course you're typically measuring a projection of this under one piece of the complex plane. I mean, in principle, you would actually try and fit the imaginary frequency component separate from the real one, which involves looking very carefully at line shapes. So
Right.
can you see that?
Well, actually, we only fit the real part, and we calculated the imaginary
Right,
part
exactly.
using the.
Yeah, so,
Equation.
I mean, no, but actually, in principle, you should be able to see that, from gain and loss spectra, right?
Yeah, right. The lines are pretty broad. Yes. So.
Yeah, by the way, I'm not doubting it. I mean, I think,
Yeah.
I don't know what else could happen, but I mean, as you see, you don't see very much in the spectrum. I think that's kind of the question.
Okay. So basically, that's all I have. And
Okay,
yeah.
thank you. So we had some questions, and there is time for more before lunch. Yeah.
Sorry. Thank you again. In your magnetic, I missed in your magnetic experiment, do you see the shift? Do you see that the shift of the lower polariton is in the other side, as you would expect for a decay system?
The other side, yes.
I mean, if you sorry, it's like slide 58.
Slide 58. Oh, this is magnetic experiment, yes.
Right, you see. Do you see already the fact that you don't have an A-square term experimentally from the shift?
Ah, I see.
Because I mean, you showed very nicely on the other system, and can you sort of see the evidence here that you actually are entitled to remove the A-square term?
Let's see. Because the theory has no A-square term, so that we cannot fictitiously add A-square term.
True, but if you had the independent measurement, I mean, I just look by analogy, but let's say if you had the independent measurement of the magnon, then you could tell whether your lower polariton or the upper polariton is asymptotically meeting that magnon. And that would tell, I mean, in some sense, that would be close to an experimental criteria to tell you whether you have the A-square term. That's just by working with analogy.
I see.
Are you able to make that statement?
That's a good point. I have not looked at that issue experimentally.
Because that would be a great way
Yes,
of
yes.
showing
Right.
non-A-square term.
Victor?
So I was wondering, if you were to do this experiment not in a quantum Hall state, but in
Yes.
some other gapless state
Yes.
in a finite field, would you see anything different? Why is it necessary to have it in an integer quantum Hall phase here? As
Oh,
opposed to
okay.
any
So
other
in the
region?
first experiment.
Yeah,
that's
no, not here, not this
Yeah,
one.
yeah.
So,
Right.
yeah.
So it depends on the magnetic field and the carrier density regime. So in the samples we have, given our experimental parameters, frequency and magnetic field, we are only able to access the integer
Oh,
quantum
that's the
Hall.
only phase you can access.
That's the only thing. Yeah, definitely we can explore the fractional regime. I forgot to.
Yeah. Sorry, can I come back to your magnetic experiment for a second. So
Yes.
what I didn't understand was what is the Dickey condensate phase? Is the statement just that you get a magnetic state? That this is an induced magnetic state of these spins? Is that the physics of the superradiant state? Is that it's an induced magnet, or is it something else?
It's a ferromagnetic state.
Okay.
Yes.
So in this case, superradiance means ferromagnetism induced by
That's right.
coupling of light
So
matter.
in the light matter case, it's ferroelectric. In this
Yeah,
case,
yeah.
ferromagnetic.
Right, okay, good. Right. Thanks. Other questions? Right, well, if not, let's thank Jim again.